The MIT Kavli Institute was actually founded back in the 1960s, and the person who was actually responsible for this building being constructed was actually James Webb, which the telescope is named after as well. And the idea from the very beginning was that what was going to be unique for MIT, this was back when the space race was on, and there was an opportunity to think about doing astronomy and astrophysics and solar system astronomy, for that matter, in space. And a lot of that involved new types of telescopes and detectors that there was a lot of interest at MIT in developing. And so when I actually did my senior thesis in the group that at that time the name was different. It was called the Center for Space Research. And the idea was to actually develop instruments that could be perfected in the laboratories here at MIT and then launched by NASA in small satellites. And that was one of the things that our group did first. The small satellites were things that I was involved in fairly early on in the 1990s when we did some collaborative programs with the Institute for Space and Astronautical Sciences in Japan. My research group flew the very first photon counting imaging X-ray telescope in space, and then we went on to build increasingly sophisticated and more sensitive detectors that were developed for other space missions, including the Chandra X-ray Observatory, which came out of our research group here. And then we also built a very small satellite. It was only about a little over 100 kilograms in mass that we actually fabricated entirely in our lab in this very building, and then launched it into an equatorial orbit from the Marshall Islands in the Western Pacific, and then used that to establish the locations and brightness of some of the very first detectable short gamma ray bursts, which we later learned were the type of object that's also responsible for gravitational radiation events that MIT's LIGO program has actually been very successful and is now world famous for the results that they've had on gravitational radiation detections. And these objects, it turned out, were pairs of neutron stars. And when the neutron stars would coalesce, as they would after a few billion years, the end result would be that when they would fall together, the energy that came out would be a flash of electromagnetic radiation in the X-ray band and the optical band, but also gravitational radiation. And that was, and little did we know when we started detecting these objects in their X-ray emission and gamma ray emission back in the early 2000s, that in 2017 they would turn out to be the precursors for gravitational radiation when that was established by the LIGO group here at MIT.